This is a video key for the Chem 111 homework that was due on Friday, September 9th. A number of people struggled with number 1, so this is a walkthrough of that problem. The first key is to read through the problem carefully and see what it requires of you. A typical nuclear power generator produces 1 megawatt of power per day. A watt is defined as 1 joule per second. Remember the prefix mega means 10 to the 6th. So we have 1.0 times 10 to the 6 watts, and it defines it that a watt is a joule per second. But it's doing this for a day, so we need to figure out how many joules it outputs in that day. This is where it becomes a unit analysis problem. There are 60 seconds per minute, 60 minutes in 1 hour, and 24 hours in 1 day. So we need a total output of joules of 8.64 times 10 to the 10th joules per day. Notice the units should cancel. If you end up with seconds squared per day, there was a mistake somewhere. The next question is how much mass loss would need to occur for this amount of energy to be outputted. So for this we can use the delta E equals delta MC squared. So we need 8.64 times 10 to the 10th joules. And the question is how much mass is required to do that. So we're going to need to divide that value in joules by c squared. And remember, a joule is a kilogram meter squared per second squared. Now here's where we're going to do a little bit of approximation to help you understand the scale of the answer you should get for this problem. Notice if we were going to single digits, 8.64 would round to 9 times 10 to the 10th. 3 squared is also 9, and 10 to the 8th squared becomes 10 to the 16th. So that tells me that I'm going to have 10 to the 10th divided by 10 to the 16th. I should get something on the order of 1 times 10 to the minus 6th. Let's work out the math and see what we actually get. We get 9.61 times 10 to the minus 7th. Notice that's almost 10 times 10 to the minus 7th, which is 10 to the minus 6th, like we approximated. The units on this should be kilograms, since by definition a joule is a kilogram meter squared per second squared. Where people had problems with this problem was not including the number of joules there are in a day, or having problems with the mass, or having problems with the entry of the numbers in your calculator. The key to the second problem is thinking about this as a net reaction. That overall we're looking at the decay of 238 uranium to form lead. And to help us out, we're going to include the atomic numbers to help us see this. The decay series in your book shows that at some points there are two choices. For example, going from 218 polonium to 214 bismuth, there are two possible routes. You could either go through 218 AT or 214 PB. But notice in both cases there's one beta and alpha decay. It doesn't matter which route you take. When you're adding these up, you don't add up every single one of these. You do one option or the other. So from 218 polonium to 214 bismuth should be one alpha and one beta decay. So if we count this all up, the number of alpha decays we need net are 1, 2, 3, 4, 5. Either one of those is 6, either one of those is 7, either one of those is 8. So 8 alpha and 1, 2, 3, 4, 5, 6 beta decays. Notice there are no neutrons in this path. A neutron would be displayed by a single line going straight down. There are no marks like that. A number of people put in a wide number of neutrons. Some people had like 120 some. Crazy talk. So one of our rules is that the subatomic particles should be conserved. So let's see if our subatomic particles are conserved. So if we count this up, on this side we have 238 in the mass numbers. Here we have 206 plus 32 is 238. All of the mass is accounted for with just the alpha particles. Looking at the atomic number, we have 92 minus 82 is 10, minus 16 is minus 6, but then we get 6 back from the beta. So we end up with a number on either side. So if you have atomic on the left and right, we have 92 on this side. On the other side, we have 82 plus 16 minus 6 equals 92. So the number of particles should be the same on either side. Most people had no problem with 2b. I'm not going to work through that one. They also had a few problems with 3a, so we will omit that one. In B, it is important that you recognize this is not linear. You must use exponential decay. You could either use the linearized version, which uses the natural log of the values, or you could use the exponential decay curve itself. Either one gives a correct answer. The last problem on this page caused a number of different problems depending on who you were and what you were doing. In this one, we need to calculate the amount of energy released from these nuclear disintegration. And we are given that it's 210 polonium and it does an alpha decay. And you are directed to a website to look up the masses. One thing that is slightly confusing about the masses in that table is they are listed as micro AMUs, so you need to convert from micro back to regular AMUs. But you can use the values as a help. We should expect polonium-210 to be somewhere just a little bit below 210. It's 209.9829. Notice they gave you an error bar which was in this position, so that's where you can stop that value. The lead is 205.9745 and an alpha particle is 4.0026. Most people had an okay time using the equation of delta E equals delta M C squared, as long as they had the right mass values. However, if you are getting energy in joules, you need to have that delta M in mass units of kilograms, which, if we convert our AMUs to grams per mole and then 1,000 grams per kilogram, notice what this does to our overall units at the end of the problem. Notice that the number that I'm going to get at the end of this has units of per mole. We get 5.21. The negative just means that the energy is lost from the reaction. Sorry, 10 to the 11th joules per mole. That's an 11, not an H. Notice, did we have a mole that reacted in this problem? Notice this is part C of a multi-part problem. That means it's all connected to the earlier parts. We did not have a mole. We did not have a mole. 1 mole would have been 209 9.983 grams. We didn't have that many grams. From B, you figured out that you had 0.5 micrograms that reacted. And we know that there are 10 to the 6 micrograms per 1 gram. Grams cancels, micrograms cancels, moles cancels. And notice we now get a much smaller number. If you did not do the unit conversion at the end, I took off a quarter. But it is important to point out that while this number is a very big value on a mole basis, on the amount that actually was in him, it's relatively small.